You're listening to Two Beers Until Phronesis, a podcast where we discuss the ideas of philosophy, ethics, religion, history, and culture. Alongside regular guests and friends, we discuss some of life's big questions over a few beers. Enjoy. Whoa, aliens.
Aliens?
Where?
Well, we don't know where.
That's exactly the point. So today we're going to talk about something called the Fermi Paradox and probably a bunch of other things as well. So it's basically the question, where are all the aliens? But before we get onto that, we need to frame the debate, I guess. So I think I'm going to let you take the lead there, Nye, and unpack a bunch of things which lead us nicely into the question, where are all the aliens?
Right. So, I mean, this is a question I've been super interested in probably since I was a kid. I mean, this is, who doesn't want to know, where are the aliens?
Yeah,
literally. And also just to bring the sort of context to humanity's place in the universe as well. It's like, it can have profound implications on the way we should operate as society and as a civilization, I guess, depending on how we come to answer this question. And so the basic premise is, as you pretty much put it there, it's like, why haven't we come into contact with aliens yet? Given a set of assumptions that, a lot of people would go, well, hey, the universe is massive. We know that life has occurred on Earth, so, surely given the number of chances for it to happen, why hasn't intelligent life come in contact with us? Because of the amount of time as well, that's, because these things happen over such massive time spans that surely if their life had started and it got to the stage of intelligent life, by that logic, surely it would also have technologically advanced to a certain stage where it would come in contact with, because the time spans we're talking about are so massive. And essentially, the phrase Fermi Paradox comes from, it's named after a guy called Enrico Fermi, who was an Italian physicist. He was actually one of the people who built the first ever nuclear reactor. But the reason why it's actually kind of named after him isn't necessarily because he was like the first person to really come up with this or really talk about it. It was pretty much just because him and his physicist friends back in the early 1900s were just talking about alien life and the possibility of all these like planets out there and all that sort of thing.
Is it comparable to the way we sometimes talk about Platonic idealism or something? So like, he wasn't the first person to be an idealist. It's just it's kind of just where it's captured in the public consciousness.
I would say he wasn't even the first person to actually speculate why, given a certain set of things, aliens haven't contacted us already. The actual paradox itself, the statement of, given these parameters, why haven't we come in contact with alien life yet? It was just kind of coined. He was named after him because basically they were around a table and just like talking about it.
We just associate it with Fermi, basically.
Yeah, and he just at one point says, "Where are they?" or something. It was the report sort of
he was at lunch, wasn't he? And
exactly. So it's vaguely something like that, and it ended up carrying his name basically. There was 1938 the Nobel Prize for radioactivity and stuff. So he was a cool dude, and so. Sort of moving forward to understand why this is a question in the first place. So why is it that people go, well, there seems to be every opportunity for life to exist? We need to have a look at some numbers. So let's go over sort of the scale of the universe, or at least let's start off with the sort of history of the scale of the universe. And so historically, I guess we were more or less the center of the universe for, thousands of years, really. It's just we didn't really place ourselves in a solar system, I guess, until maybe a few thousand years ago. It's kind of hard to say exactly what people sort of meant by a sort of system, but either way, we were sort of proposed to be at the center of it, and there were these celestial bodies out there somewhere that was kind of part of this like sphere.
Heliocentrism is quite a novel concept in the history of humanity, really, to suggest that the sun is the center of the universe as opposed to us. And it's the same on pretty much every level in terms of, because I know when Freud started talking about the subconscious, that turned a few heads in very much the same way that heliocentrism did, that man wasn't even in control of his own mind, and especially the way that people started to talk about consciousness, that it was possible for consciousness to be elsewhere. Yeah, I think for a long time, especially with Judeo-Christianity, we just assumed that not only are we at the center of the universe, we're the only thing like us, and it's impossible for anything else to be like us. Our significance is paramount and unique.
Right. It was sort of like this demolition of the ego of man in some sense, or at least one of them, which came about during the Copernican Revolution, which many people have heard about, which is sort of like the 1500s going into the 1600s, with a few different historical figures noted for that, which put the sun at the center of, well, at that time, the universe. That was the whole universe, was this sun at the center of the universe, and the celestial bodies and the planets all moving around the sun. And it wasn't until around 1775 that the philosopher Kant actually proposed these things called galaxies, which were disks of stars, basically like the solar system, but just on a star level. And he even went so far as to say that some of these sort of fuzzy patches, some of which would later be thought of as nebula and things like this, were actually whole other galaxies, which he called island universes. Because he was a philosopher, they didn't really take his ideas seriously.
I was going to say, did he have any evidence for that?
No, he didn't, and he didn't really. He wasn't really making observations. He was kind of just like, idea, well, okay, you've got all this stuff everywhere. What if it's like the solar system, and it's like the whole thing is like a giant solar system with all the stars?
Yeah, it's just nebulous ideas. Because I guess empiricism hadn't really been cemented yet, the scientific method.
Yeah, this is sort of, during Enlightenment, sort of just after, during, whatever. We're talking, during that sort of era where the scientific method wasn't really like a formal thing. And also, I mean, especially when it came to the cosmology and the universe, our ability to measure these things empirically was coming along slowly, let's say. But the next biggest steps did come in the 20th century, and one of those sort of bigger names in increasing the size of our universe was a woman called Henrietta Levitz, who in 1912 found out a way to measure distances to things by using things called standard candles. And this is where the idea of a standard candle is essentially just a thing that is consistent enough that you can use it to measure distances. And the things that she originally used were what called Cepheid variables, which were stars that just sort of pulsated in a certain way for various reasons. And you can use that to determine distance based on how faint and whatever it is. But you couldn't really do that until you figured out exactly how bright a Cepheid was at a certain distance. So unfortunately, you couldn't use it to measure distance until you knew how far away one of them was. So what you actually do is you use parallax, which is essentially where as the Earth moves around the sun, obviously the night sky sort of changes position because the Earth is a sort of a slightly different position, and closer stars will move more relative to the Earth because of how the Earth is moving through space. And so you can use that yearly variation to see which stars move the most, and because of that increased parallax, you can tell sort of how far away you are from those stars. And then you do that with a Cepheid variable, and you're like, oh, hang on, we know exactly how bright this one is supposed to be at a given distance. And so we had a standard candle, and then sort of later on, they started measuring these globular clusters and things in the Milky Way, and suddenly the sun was no longer at the center of the galaxy, at least for a while, although this was definitely debated. And it turned out that the Milky Way, or the galaxy, was way bigger than they first thought. And the first sort of measurements using these standard candles sort of come in, and they started to... the first sort of readings were around sort of 30,000 light years across. We'll get to sort of how much a light year is, and even though it's just a really, really, really long distance. And so they were like, Jesus Christ, that's like 30,000 light years. And then eventually, using better techniques, they found out that they were getting measurements like 100,000 light years across. And at this point, the Milky Way was still the entire universe, with this idea of our galaxy was still the subtotal of reality. And it wasn't until later on that essentially observations were starting to be made in Andromeda, one of the nearest galaxies to us. They were using things like novas. Novas are basically, without going into it, they're sort of where a star and it's the star nearest to it as well, star in the system starts pulling material off of it, and that material causes like an explosion, basically, or like a big boom, a big bright light, and you can use that because it's fairly consistent. You can use that bright light as a standard candle. So you go, well, how bright was that flash? Well, we know how far away some of these bright flashes are. So if we look at how much fainter some of these even further away flashes are, we can calculate the distance. And then so they started measuring them in Andromeda. They're like, oh, hang on a minute. that's really far away. That can't be right. It wasn't until sort of like 1926 where Edwin Hubble actually some serious science on it and started to measure these little bright flashes and things in what at the time were sort of referred to as spiral nebula, because they thought they were just like nebula, basically these big sort of fuzzy patches in the sky. And he realized that, oh my God, these are galaxies in their own right. These are actual whole systems of stars, and they're massive. I don't have I think the figures at the time, we're talking, he was calculating maybe 500,000 light years to how far away these things are. And to reiterate some numbers again, the calculations for the Milky Way were like 100,000. So suddenly something being 500,000 light years away was like, oh my God, that's huge. And to give you reference, the actual distance to Andromeda, as we measured it now, is about 2.5 million light years away. So, about 5 times bigger distance. But at the time, this was, oh my God, there are other bodies of stars, these other sort of island universes out there. And going on to the 20th century, obviously our telescopes got better, our methods got better, and the universe got bigger and bigger and bigger and more galaxies until we essentially have what is now, we started using things like type 1A supernova to actually get better standard candle measurements again. So we've got more consistent ways of measuring the distance to things. And with that, all sorts of like crazy things happen. We discover that the universe is expanding, etc., etc., etc. So the universe became massive.
Yeah, massive so quickly as well. That's crazy. Yeah.
Yeah. In 100 years, we went from thinking like the Milky Way was like the entire universe to going, oh my God, like the observable universe now. I mean, roughly speaking, is about 46.5 billion light years in radius. So it's like about 46.5 billion light years to the edge of the observable universe.
And it correlates with fucking everything. The invention of decent sci-fi and the decline in Christianity. It's just, because it's so sobering to think that.
Demolition of the ego of man continuing and compounding. And so these massive numbers start getting in, and I mean that's just like talking about billions of light years already. That's just ridiculous numbers to give you an idea. And obviously that says that the amount of matter that's distributed what's called it's homogeneously and isotropically, so it's relatively consistent on a macroscopic level how it looks. That is a hell of a lot of stars, a hell of a lot of galaxies, a hell of a lot of potential planets. So let's talk a little bit about calculating some of these actual things that go into the Fermi Paradox, given how large this universe is. And so essentially how they started to sort of formulate one of the heuristic ways of doing this is what often comes up is called Drake's equation. Or the Drake equation, I should say. It's not the Drake's equation. I keep calling it that, but it's the Drake equation, which was a thing that came about in 1961 by Frank Drake. And it was just basically a way, he originally made it as a way to facilitate discussion at the first SETI meeting. SETI stands for Search for Extraterrestrial Intelligence. Which is sort of, and this Drake's equation sort of became one of the backbones of astrobiology. And it's just an approximation. It's just a way to like plug in numbers and kind of get start to make vague, sort of create discussion about can we actually come to any idea of if other life is out there. And so to break down this equation, essentially it's about 7 different terms in it. And it starts with sort of just like it's n equals, and N stands for like the number of civilizations in our past light cone that we may be able to communicate with. Past light cone essentially just means within
our galaxy.
It's more fundamental. It just literally means within a fundamental causal relationship. So it's like because of the speed of light being sort of like essentially the speed at which causality can happen, there is a limit to how far you can communicate before it becomes impossible. Given the speed of light, given the expansion of the universe, all these sorts of things, we're actually pretty much, if FTL isn't possible, we are restricted to, at best, our local group. There is no possible way. It's completely impossible, according to our current understanding of physics, to go any further because of expansion and all because that's just a limitation of the speed of light. So past light cone is kind of like, okay, what's the maximum? If light traveled for that distance, into the future, like can there still be a causal relationship?
Right. So I read this, and I don't know if this is true or this is even accurate, but there are 10,000 planets for every grain of sand on Earth. I don't know who's counting
I'd
the
have
sand.
to look at the numbers of like what people think sand is and all that sort of thing. Is that the observable universe? Does it say
I've just got there are 10,000 planets for every grain of sand on Earth. That's in the Milky Way, and a fifth of those have an Earth-sized planet in the Goldilocks zone, which I guess we'll talk about.
We'll talk about some of those numbers in a minute. I mean, like that's a good like sort of place to say like how massive these numbers get and how ridiculous they get, and
potentially trillions of habitable planets.
Yeah, and so the Drake equation. I mean, the factors that go into trying to calculate this, the communicable distance that intelligent life could be at, is one. The first one is simply the rate of star formation in our galaxy, which kind of makes it how many stars are there forming in our galaxy over a certain amount of time. The next term is just the fraction of stars that have planets. So the next thing to sort of calculate is, okay, how many of those stars actually have planets? And then the next one to calculate, the next term, is how many of those planets can actually potentially support life. The next calculation you have to do, the next probability you have to add is, or multiply into the equation, is the number of those planets that actually develop life. So like, that's another factor you have to add as a probability. The next one is that the fraction of that life that can actually become intelligent.
Yeah, it starts to get very vague and difficult. Yeah,
it's already extremely vague and difficult. But it's all of these things are sort of like ways to sort of discussing or thinking.
As an approximate. Yeah, it's good groundwork.
Yeah. The next term is simply the fraction of that of that intelligent life that emits detectable signs of itself into space. Traditionally, we sort of think about that in terms of things like radio emissions and things like that. And the final term is simply the length of time that those detectable signs have been released into space. So it basically, because of the fact that, again, there's a fundamental limit to the speed at which radio waves can travel, the speed of light, they have to have been traveling for a long, if it's far away, they have to have been traveling for a long time before they will become detectable by us. So those are sort of like, that's the sort of ground basis by which much of the calculations, much of the way we sort of facilitate a discussion about those. Of course, we'll talk about how there's some more nuances to that equation.
Yeah. So how useful was this at the time?
Well, considering there was no real way to talk about, realistically talk, even like facilitate a discussion about how you would go about calculating the probability of intelligent life out there. Yeah. It's useful in that sense that it is just like, okay, well, here's just a formal way of just quickly getting us off the ground to a point where
frames the question, conceptualizes.
So we can actually talk about various things and what we think about these particular terms in it, like whether we think they're completely uncalculable or whether we think there's actually a way we can plug in numbers and start to get an idea. And so, I mean, our own radio waves that have traveled at the speed of light is, we've been chucking them out for about, between 100 and 200 years now. And there's not only is it unclear how far these signals can go, but that is essentially a couple hundred light years that we have a bubble around around Earth. And in the scale of the universe, that is not very far. That's not very far at all. Proxima Centauri is about 4.1 light years away, which is the nearest star to us. And aside from other stuff that we've sort of chucked out there as far as like us trying to make an impact on the universe, we have, things like Voyager 1, which is now, 150 astronomical units away from Earth. And we'll sort of get down to what those sort of scales mean. But an astronomical unit is about 150 million kilometers, which is the distance between Earth and the Sun.
I think this is complete bollocks, but I heard that we chuck out that hoping that the aliens go da-da. That's what I heard.
Do we? Oh, that might be a weird METI thing that they do. METI is messaging extraterrestrial intelligence is what it stands for.
Yeah.
It's like a subset of, the SETI thing where it's like people who actively broadcast
Do we still do that? They're still like...
Yeah, I think we do, yeah.
Like
I don't actually know a huge amount about METI. I know that we are still broadcasting, obviously. We're still making noise. As far as like active attempts to, aside from just broadcasting radio signals, I know there are places that are literally sending out messages into space deliberately just to send these radio waves out into space as like little packets of messages. And we actually sent out all sorts of message. I mean, the first two Pioneer probes, that was 1972, 1973. We had like little aluminium plaques on them with like loads of information about, us and who we were. Some of them you may have seen. The more famous one you've probably seen at the Voyager Golden Records. There's a lot of people have seen, which were just little phonograph records that had like sounds and images, and it was just basically just like a catalogue of the diversity of life on Earth and our culture. Sort of like it's a time capsule, basically.
Have you seen that fucking terrible film Pixels?
No, I haven't.
The aliens basically come across like a time capsule of like retro games, and they think it's like a threat. So they it's an Adam Sandler film, and it's fucking awful. And they like the aliens like take the form of like Pac-Man and Donkey Kong and like destroy us. Yeah, it's fucking
wow,
useless.
I'm so happy I know that now.
Yeah.
Great.
The more you know, the more you know.
Yeah. So moving on to like actually trying to calculate, like you're mentioning how many of these planets there are potentially, and I mean, in the observable universe itself, like going off again, we're already going to go off with just crazy numbers that are complete sort of like massive error bars on these. Like I often like to preface on things we don't really know, but giving it a good guess, the number I've managed to pull is 1 billion trillion stars in the observable universe.
So that's 10 followed by 18 zeros.
Yeah, something like that. It's just ridiculous. Yeah.
So I've got here that yes, it's 2 months after the Drake equation sort of came out. Harvard University astronomer Harlow Shapley basically calculated the number of suns in the local group.
Yeah. So as I sort of said before about the sort of history of our size in the universe, like Shapley was actually a big part of that story in terms of like measuring distance. I mean, originally he actually, I believe if it was Shapley, I believe he was the one who was actually a proponent of the Milky Way being the universe. He was actually originally against the idea of there being all these, the universe being this massive thing with lots of, island universes, so to speak. And there was a whole great big debate staged around that as well, which was kind of interesting. So what was your original thing about Shapley again?
So 10 million suns, and 1 in a million of those has planets around it.
Right. So, I mean, the modern calculations for the local group, which is sort of, again, our sphere of influence that within reason is kind of in our past light cone. That's galaxies like Andromeda, and there's Triangulum, which is like the third biggest sort of structure in the local group, and things like that. I mean, I have absolutely no idea. I don't think anyone can really know, because there's so much of our local group that's absolutely obscured to us to even detect. But Andromeda, for example, has 1 trillion stars in it. Triangulum has like 40 billion. But focusing on like the Milky Way, we've got up to about 400 billion stars, and sort of as low as about 100 billion stars in the Milky Way, to give you an idea. The observable universe that massive, again, like 1 billion, like just a ridiculous number. But focusing it on to sort of, where the question is, okay, alien life within possibility of travel and that sort of thing. We're talking hundreds of billions of stars. And so the next thing you factor into that calculation, okay, we've got hundreds of billions of stars. The next one we want to figure out is essentially, well, how many planets are there? How many Earth-like worlds are there even? And so there are a few interesting ideas on how we start to pass this question. I mean, one interesting idea is actually this idea of the galactic habitable zone. So you may have heard of a habitable zone around a star, the point at which liquid water can form, and it's not too close to be tidally locked and all that sort of thing. And there is actually sort of a theoretical, and this is kind of like a hypothetical thing that's been, I'll get into the sort of criticisms of it, but there's a sort of habitable zone in our galaxy that essentially is about factors that, like metallicity and the rates of supernovas. So if there's loads of like supernovas going on, loads of explosions and things like that, obviously that's going to create a much more tumultuous situation for a lot of planets. You can have things like, if you're too close to like a supermassive black hole, like Sagittarius A in the center of our galaxy, that can emit tons of radiation, like high frequency radiation, and also you can have like in really, really high sort of star density areas, like in the bars or like closer to the center, you can have more sort of gravitational perturbations. So you can have as more stars kind of interact with each other, that can cause disturbances and things like the Oort cloud and things like around our solar system. You just basically cause shit to fly everywhere, and that can create more potential impact events for meteorites and things like this. So there's a sort of zone where you don't want too much density, and you want metals. You want certain elements to also be abundant. So it's more likely for these sort of these metal rocky like terrestrial planets to actually form. And it's one of the numbers I actually sort of came across. It could be as low. I think it was between 10 and 20% of all stars are in the galactic habitable zone. So that's already really narrowing the search if we think about this as like a reasonable idea. But it has been sort of criticized. I mean, apparently, there's things to say like stars do actually migrate quite a lot in the solar system, or possibly do. And also it's like quite poorly defined what the exact criteria for what would make a habitable zone, or whether it even is like a reasonable assumption to say that a star or a system has to be within the habitable zone in order for planets to be more likely to be habitable. But it's it's another way to sort of think about it. But taking all these sort of stars that may work, we need to actually find the right kind of stars as well. And so our sun is what's called a G-type star, which is just a type of star. It's a yellow thing, and it's relatively stable. It's sort of like in the middle period of its life. It's not going completely mental. I mean, like Proxima Centauri, for example, which is a red dwarf. It's basically a lot of the planets around that are very inhospitable, or at least from what we currently know about them, are not great candidates for being able to be habitable as far as we know, because of things like solar wind, because it's quite a violent star. It just emits loads of crap. It's quite violent.
So how typical is our star?
Pretty damn boring. Yeah, we G-types, or at least sort of main sequence, as they're called, these sort of like these stars that are fairly our sun is very boring. It's very typical in our galaxy.
And so there's a lot of G-type stars.
Yeah, there's a lot of them. I mean, assuming essentially the figure, I've seen a 9% figure, which I think is more of an older figure for the total number of stars being in this G-type category. The one I've seen that's from a more recent thing I read was set about 7% of all stars are sort of G-type in our galaxy. So assuming that, and assuming a mid-range, value, we said earlier the Milky Way has between about 100 and 500 billion stars in it. So let's say about 250 billion stars. That's about 17.5 would be in this particular G-type star that's not particularly violent. And up to a maximum, let's say there's like 500 billion, that's 28 billion G-type stars, and that could be as low as about 7 billion G-types, just to give you some like idea of the error bars on these sorts of calculations. And then within that, due to sort of recent observations of exoplanets and things like this, we started to come to an idea of roughly about 1 in 5 of these stars will probably have sort of Earth-like rocky planets.
Yeah.
So that the factor is about 0.18 of these stars will have. So let's take those numbers again and plug in the maximum. Let's say, okay, we plug in, what's our maximum? We were talking about 17.5 billion was like the upper bound. Taking that, the maximum number of these habitable worlds would probably be around 5 billion. Basically less than 6 billion in a habitable zone. So
even if 0.1% of those had life, we'd still be talking about fucking a lot, a lot of planets.
Yeah, no, that's a huge number. I mean, it is narrowing down, but it's still a massive number. We're talking billions. I mean, the mid-range estimate's about 3 billion, and just the minimum bound that I could sort of, but if all these numbers are not looking great, we're talking about a billion, at minimum, a billion, maybe a tiny bit less if the galactic habitable zone thing has more merit to it. But
I'm just going to go back to that. How do we know about things like solar winds? Like, how are our instruments that refined? How are we actually getting that information? Is it
studying the sun? I mean, like we have. There's like things like the Parker Solar Probe. I can't remember the name of the mission now, which is bugging me. But there's fairly recently we launched a sun mission that's going to be one of the man-made object that's going to get closest to the sun and do a lot of direct observations.
So studying our sun, and then
studying our sun,
extrapolating that onto
mostly.
Others,
I mean, that's probably where we mostly know things about stars. Obviously, we can learn a lot from looking at things like the spectra of stars, which is the sort of essentially the color of light it emits, or like the frequencies of the particular light it emits, and we can use that based on what we sort of know about stars and things to figure out stuff like what is the process going on inside them, and how these things would would behave. So yeah, a lot of it's observational based on our own sun. I mean, we can obviously look to a certain extent at the effects that stars, other stars have, and things like this. Yeah, we know. We don't know everything, and like again, we can't. There's still lots of things to figure out, especially about like the extreme ends of.
Well, I guess you see a fucking supernova, and you know that okay, that's probably not going to be conducive to life. Yeah.
Well, giant, massive solar system size explosion, probably. Probably not great for life. Well, unless you're talking the aftermath of it forming planets in a new system. But so. Taking those numbers in, we got at least 1 billion as up to like nearly 30 billion, these Earth-like planets that are in sort of habitable zones. And taking those, and this is, by the way, excluding things like moons, we're excluding other potential things. We're really sort of narrowing it down here. Like I sort of like gave the local group a go, but we don't have enough data on like how many stars in the local group. So, but I would say we're talking about potentially hundreds of billions of these Earth-like worlds just in the local group. So the next sort of parameter, I guess, that's like one of the other sort of defining features of the Drake equation is the biological aspect of it, is the idea. We've got like this massive number of potential sites for which life can arise. So, how does life arise? I mean, is it what do we know about life on Earth? What do we know about how things actually kicked off here? Can that tell us anything about the likelihood of life developing on other worlds? Before we do, I'm literally just going to set a definition for life. This is NASA's definition for life. This is what we're going to be talking about for life, because obviously at the limit of how we define life, that is a whole another podcast in itself. Potentially that would be an interesting podcast to do. What is life? There's lots of people who are, furiously debating this question and trying to find a better definition for what we call life, especially when we get to the limit of things like viruses and the origins of life. But for now, life is a self-sustaining chemical system capable of Darwinian evolution. That's nice. That sets us a nice little parameter. And essentially, all our cells are made of chains of amino acids, which fold into proteins and things like this. And we have DNA, which is replicated through RNA, which is made into these proteins. These amino acid chains are converted into these proteins that build us up. And this is roughly what's called the central dogma of biology, very, very roughly. And so going into sort of like proposed origins for life, I think the leading candidate, certainly there hasn't, at the moment, there isn't really, there's nuance to this, but at the moment, what we think the origin of life kind of, one of the hypotheses for how all this sort of, pillar of biology kicked off, is what's called the RNA world hypothesis. And so it's thought that there was some, primordial soup, which everything sort of kicked off in, which is essentially just like a chemical environment in which there's lots of these things called nucleotides, which are the building blocks of RNA and eventually DNA. And first thing you need are these nucleotides. You need them to start sticking together. You need them to start bonding. And the RNA world hypothesis essentially says, well, if you get some of these RNA chains, RNA is sort of like DNA split in half. It's got a different nucleotide. DNA, one of the nucleotides is different. But all you need to know is it's a bunch of different nucleotides, 4 different combinations you can make, and you can get chains of them. And they can bond with other nucleotides and things like this. And so you have a basic thing that's swimming around in this soup, picking up nucleotides, creating chains, whatever. And so essentially what you get from that, what the hypothesis sort of suggests is that, okay, you've got this thing all happening stochastically. So it's maybe we can assume that some RNA strands that are more stable, are stronger at surviving and sticking together, would be more likely to stick around. And then, extend that idea. Maybe because these RNA chains can stick nucleotides to themselves or encourage more nucleotide-y kind of environment, they can start copying themselves. And there's mechanisms through which this RNA can actually start copying itself. And then obviously you've got a sort of Darwinian mechanism going on there where this copying process can eventually lead to something. And obviously there's a clear threshold here that we don't really know about. That's just a hypothesis that leads at some point into an actual cell, an environment which some sort of lipid structure that basically creates a barrier between this process of copying and the outside world. We know that these sort of structures of, if molecules want to, if they're sort of dipolar, so to speak, they're like, essentially one side of the molecule is, I can't remember the word now, but it doesn't like water. The other side likes water. Hydrophobic, sorry. If they clump together, obviously they're going to want to keep the water out. So you can see how naturally these things with these properties might actually just create these little membranes and things just by happenstance because of their properties. And at some point, perhaps you get RNA structures, you get these weird things that are like replicating or creating a more RNA-ish kind of environment and selecting for themselves, end up inside these cells. Yada, yada, yada. At some point, somehow, that's how you start to get actual cells and life. And
You're telling me Prometheus isn't real?
Oh no, Ridley Scott.
Is it not giant big blue men?
Giant blue men. Yeah, well, I mean,
so obviously the question is,
this is a hypothesis. So Ridley Scott's hypothesis is a hypothesis as well, that it was giant blue men. I mean, you pick one,
That film is many things. A hypothesis probably isn't one of them. But so obviously the question is this process, is it unique to our world, and is it something that can happen on other planets?
Well, unfortunately, the selection biases here. This is, given what we can piece together, this is what we think is like the most currently the most likely hypothesis for how this stuff came about. But the problem with that is obviously we're limited to knowing this about the particular chemical conditions in which this arose. So we can only assume, we need these nucleotides, we need these amino acids around to build proteins, and we need particular conditions in which these chemical compounds can actually survive and not break down or not just get completely yeeted.
How far can that stretch though? Because obviously there's things like cockroaches. How far is that stretching? What is needed for life to exist?
Yeah,
is that?
This is the thing, is we'll get into that, but like exactly that's one of the things, is we don't know. But of course, if we're being very, very rigid and going, okay, well, we know this is how it happens, and we're like, well, okay, if this is our criteria for how life starts, it has to be something like this because this is the only mechanism we know of. Of course, there's a bias there because we are the only sample size we have of life.
I suppose we're talking about intelligent life as well.
Right, and then there's further on, but as far as
spacefaring life and life that's capable of communicating with us, it's no good thinking about like sea creatures or whatever, because that's not really what the Fermi Paradox is addressing.
Right, but we're starting off with our assumptions of, okay, well, this is a mechanism. We know life is here, so we know that at very least in our sample size of 1, this is kind of what life looks like, and this is what life kind of is. So the conditions in which it arose are the only conditions we know of in which it can arise. So it's, that is a big assumption that we have to make, or at least we do make. Not everyone does, and that's, we'll get into that in a minute. To give you a sort of timeline of what sort of happens, I mean, this is all we're talking right at sort of the end of what's called the Hadean, which is like this about 4 to 4.5 billion years ago. Right at sort of the verge of when the Earth started to become what we would call habitable, or suitable for these conditions to happen. And potentially this RNA was sort of floating around 4 billion years ago, and it's kicked off this whole process. And at around what's called the Archean, we start to see things like the first fossil evidence for prokaryotes, which is the first sort of actual place we can start to go, okay, this is where prokaryotes exist. Prokaryotes, I should say, are basically bacteria. They're essentially a cell which doesn't have a nucleus. It's just sort of like a cell that pisses around. And prokaryotes were like, the very first thing that's like much more recognizable for what we would say is life now. That's around 3.5 billion years ago in the sort of Archean eon.
I keep seeing articles, and I don't know if they're real or not, bloody asteroids from Mars and pieces of moon rock and stuff that like might have things on them that might like lead to life and things. Is any of that? Is there any truth in any of that? Or
well, so I think there's a few things there's a few things in there. I think one of them is I don't think you're talking about is panspermia, which is the idea that life came from an asteroid or another world. But we'll get into that in a bit. But yeah, I think what you want to be talking about is like when they discover things like amino acids and or what's even more generally, they discover organic compounds, which are essentially the things you need in order to start building these building blocks that life as we know of needs to exist. And so what you'll generally probably be hearing is the fact that they've discovered some of these chemical properties, like they've discovered amino acids, or they've discovered like, and that doesn't mean life, but it's just like
the ingredients for life.
It's an ingredient you might need. So it's like we can see that these particular chemicals aren't like unique to Earth, certainly not. I mean, even recently we discovered some amino acids in this is actually within the last couple of days. So this is some fresh news off the podcast. I mean, it's the 1st of November now. Okay, it was the last couple of days. There's been like some reports on amino acids in Venus's atmosphere, which doesn't necessarily implicate anything, but it's just like, oh, that's cool. So there's actually there's actually some interesting things. And before that, obviously there was a discovery of phosphorus, and we're still trying to piece together how the hell phosphorus actually ended up on Venus, because at the moment we only know of mechanisms, non-biological mechanisms to produce it. Phosphine. We only know of non-biological processes that couldn't exist on Venus. Like we actually see it in places like Jupiter and whatever, but we know that's because of the extreme conditions there. So that's an interesting ongoing thing. But yeah, so like. Yeah, well, a lot of what you're probably hearing about is like, they're discovering some of these chemicals or some of these things. That doesn't have necessarily anything to do with life. That just means that, just means it's got some of the same chemicals that early Earth did. And perhaps these, organic compounds and amino acids and things are not as rare in the universe as, as we maybe might have thought. And so sort of moving forward, these cells, like the next sort of big event, I guess, sort of zipping forward through billions of years, which, by the way, is a massive amount of time for life to just be sort of these little single-celled things, is essentially when eukaryotes happened. And eukaryotes are essentially what we're made of. They're what plants are made of. They're what bees are made of. They're what fungus is made of. They're what literally, it's still... In biomass, they're about equal to prokaryotes, but prokaryotes, as in like bacteria and things like that, are still the dominant. They're still far more prokaryotes than eukaryotes. But in terms of like biomass, eukaryotes are like, are still big players. And obviously you get all the variation of life that we sort of observe directly in our general lives are eukaryotes. So eukaryotes are essentially basically where you get, they're defined as just a cell with like a closed nucleus, because prokaryotes don't have that. And they also frequently have like other what are called organelles, which are like essentially little cells in themselves inside this bigger cell. And the event that this is about 2 billion years ago, we think that the first very, very roughly about 2 billion years, that first eukaryotes came onto the scene. And the proposed hypothesis is simply at some point, a little cell went into another bigger cell, and then it went, oh, I'm still alive. Cool. Let's work together. And then suddenly you get things like mitochondria, or in the case of like Animalia and things like this, and we actually know that this happened independently at least 3 times. These cells got into another cell, because the second example we have the chloroplasts, which are essentially the equivalent of mitochondria, but for the plant world. So at some point, another little cyanobacteria got into a cell and started converting light into energy, and the cell was like, "Oh, cool, dude! I'm not going to break you down and eat you. I'm actually just going to like." Somehow they didn't just eat each other. It started this like weird little relationship.
I read somewhere life basically originated from 4 places, 4 genuses or whatever. Only one of them now exists. We have evidence of the other 3. and that's kind of why sort of 2 eyes, spine, whatever. I think 80% of life is one set, and then 2 of them are extinct, and the other one is like deep sea creatures. So that's like the other 20%.
We're going right down to like phyla and things like this. I think now. So I mean, obviously there's lots of different divisions for life. You've got things like what I'm sort of talking about now is the kingdoms, and then you've got like domain kingdom, and then like class, and then phyla, and then it goes on and on. I can't name all of them off the top of my head. But essentially, depending on where your measuring stick is, yes, if you look further back enough, you'll find that like the vast majority of a particular clade or phyla or whatever has been condensed down to a small set of a branch that it sort of came across. And at this sort of resolution, we're talking about domain, basically, kind of kingdom, which is essentially where the separation between these 2 very different kinds of cells. The third one in this being archaea, which is slightly different. They're sort of like extremophiles and things. They're weird bacteria, basically. And so like this eukaryotic cell thing is what is this theory is sort of called endosymbiosis. In fact, fairly recently, there's been some interesting stuff about viruses having some kind of role. I know there's proposed theories called like viral eukaryogenesis, which is like where viruses also have a role to play in this weird cells all working together thing. And so that's another weird event, and that led to all of animal life. Very quickly after eukaryotes, that's where you get multicellular life. Multicellular life, not a thing. And then eukaryotes rock on, and within, let's try and find a sort of timeline for this. Within, I think it was like a couple 100 million years. About 500 million years. So 500 million years after eukaryotes, you start getting multiple, which relatively speaking, it's billions of years of just bacteria. Eukaryotes start up, and then you got 500 million years, multicellular life starts becoming a thing. And then there's just like this, things really start kicking off. Then you've got the sexual reproduction, fungi, eventually plants and animals start appearing. This is all going through what's called the Proterozoic, which is about 2.5 to about 0.5 billion years ago, 500 million years ago. And then already we've covered like 4 billion years already, and we've only just got to like things really kicking off. And this is where we enter the Phanerozoic, which is, everyone's heard of the Cambrian explosion, 41 million years ago, roughly. This is when we start to see all the major phyla of animals all kicking off, and this massive amount of diversity occurring. And from then on, we don't have to go through every fucking every era of biology here, but essentially that's sort of like the story of life, and you can tell already that there's massive timescales involved. We're talking billions of years, and not only that, but with billions of years, there has to be a few criteria in there that have to go right for this to happen, and some things that on as far as these timescales are concerned, look kind of it's a long time for things to only be in one particular way. And I
think as we talk about intelligence, that whole timescale thing is going to come back again, and timescales are very important to this conversation, I think.
Right. Well, let's just talk about intelligent life before we start getting this. Just the last little bit before we start talking about like solutions to this paradox.
By the way, I opened your beer, and
thank you.
We're on an hour.
Oh, good. We're almost at the answers, so that's fine. Almost there. Okay. So, I mean, intelligence in evolution, that's sort of like the next thing I guess we can start to talk about is the fact that we also only really have one example. We only have one example of human level intelligence in evolution. And it's one of those things where, looking at it at face value, it may actually require a lot of luck for us with these ridiculously oversized brains to come about. There's no examples of what's called convergent evolution with our level of intelligence, where you just got these brains that are just capable of a ridiculous level of abstraction. Big brains are like extremely highly demanding in terms of energy and mass. Like it's kind of crazy, like how much energy we've like teched into evolutionarily just to keep these things running. Not only that, but like means we have massive heads, which are kind of annoying. It means like, it causes problems with giving birth. It means that our infants are just like completely useless for a long time, as we have a really long sort of development period compared to a lot of animals.
Yeah, I mean, you look at a gazelle, it's like a half a day old and it can run like as fast as a sprinter.
Right, it's crazy.
What the fuck can you do with that age? Cry.
Yeah, literally nothing, yeah. And not only that, but we also we're lucky we have cultural evolution as well. It's like, it's not just the fact that we're born and we're computers. It's like, that's not good if you can't pass down information, if you can't build on a collective understanding. So that's another really important step into our processes as in intelligent beings. Extended
phenotypes and things.
Yes,
something I know.
Yeah, I think we mentioned that briefly in our.
What is philosophy? I think that's that episode.
Somehow that's got into what is philosophy. Yeah, I mean, it took us about 200,000 years to get where we are now, evolutionary speaking. We're the first sort of hominids and things, and all of this is a big lucky. We need a big lucky streak to get to that point without potentially going extinct. And and humans are weird. So that's roughly, I would say, all the random criteria that we just to set a basis for like all the things that go into this idea of the Fermi Paradox. Like, okay, why aren't there aliens given all these things? We see life on Earth, and there's an astronomical number of potential sites for life to exist. So what are some of the answers proposed to the paradox? Why haven't we come across any aliens yet? And I'll just rattle off the titles of how I've sort of categorized some of them. And then we'll talk about this. So we'll unpack some of them. You can, and then I can shut the fuck up for a bit. We can actually
take a breath, and have a beer.
Yeah, I can actually drink a bit. So I mean, the first one I would put under the category of sort of rare Earth hypothesis, which is a sort of separate thing. But rare Earth hypothesis is essentially, just in a word, we are super lucky to have these particular conditions in which life, there's like loads and loads of factors that go into Earth being a perfect sort of, a place for life to evolve, and that's quite rare. Another one, which we'll dig into in a moment, is great filters. We'll get into what those are and what those mean in a minute. There's essentially, I just put literally a bullet point of, we lucked out so far on previous extinction events, which is kind of like filters in the past. Like, we've already passed some things that should have killed us, but somehow we got lucky and got through them. And ordinarily that should happen much more often or something. Another one I have is that that aliens out there are just think that we're too primitive. Well, actually, we're too primitive to send out messages that are actually detectable to advanced civilizations. So that our radio waves just don't even care.
It's like sending Morse code out to a world of bloody Snapchat and things.
Yeah,
I'm such an old man, but like I still use Morse code.
Yeah, that's how I knew what time to come here. Yeah, to do the podcast. Send me a bill. Yeah. And I sent you signal back in smoke signals, and another one is, so intelligent life eventually does not broadcast much radio signals as their technology becomes more advanced and noiseless. So this just basically is like what we're detecting. We're looking for signals that an advanced civilization may actually just not be leaking out anymore because of things like maybe they just start using much more noiseless technology that just doesn't leak as much shit into the universe. Maybe they do use stuff like neutrinos to actually communicate information. Things like this.
They all use steam and magnets.
Yeah. I've got a whole category here, which I'm not going to... I'm just going to give you the title, which will break into the different ones in this category, but I've just put sneaky aliens. As one of there's lots of different ones under this category to do with why they're sort of essentially hiding from us. Another one is sort of loss of motivation that I sort of have another thing, which can essentially be to do with a civilization, essentially at some point, for whatever reason, and we'll get into different categories of how this can happen, just have no motivation to go out into the universe, travel, expand, do anything anymore. There's no longer a point for them to do it. Another one is essentially simulation hypothesis stuff. So, we're getting down that rabbit hole, but it's what's broadly under this category called the planetarium hypothesis, which is to do with, it's a simulation. So, more or less sort of answers itself. That's why there's nothing around, because it's been designed this way. Another one would be interstellar travel may actually be even more technologically unfeasible or even impractical then we actually think, despite the rate of innovation, we may actually find, it's sort of, interstellar travel over vast distances. Obviously, we can't go as far as we know faster than light, but even over sort of long time periods, slowly expanding out, we may actually find that it's just so economically impractical that it's actually we're not really properly calculating the capacity for even advanced civilization to travel out. And the final one, I've just got X Files theme. They're already here. And that's the other answer.
Lizards.
Yeah. So those are all the sort of different ones. Is there any particular one that you want to sort of break down first or sort of talk about a bit? Should we do great filters?
Yes, I think filters is a good place to start because it frames a lot more of the stuff. So yeah, like you said, they're grouped differently. You've got filters of the past. So what are some of these events that we've supposedly bypassed and we kind of haven't realized our own luck? What are some examples of those?
Right. On here, I've sort of got filters in the future, filters in the past. So in the past category, we've got major extinction events that are pretty crazy. Let me just bring up all the different extinction events I've got on here somewhere.
So we've had a few.
Them all. But essentially, there are. It's all in the Phanerozoic category. There you go. Yeah, Phanerozoic era is basically just animals till now, essentially, since Precambrian explosion to now. And since then, we've had. I mean, the way we categorize extinctions again, it's kind of an extinction is.
It's 50 years,
defined.
Isn't it? Is it?
No, it's vaguely defined. It's just literally a massive loss of life over a certain period of time. There isn't really. It's just a massive event in the fossil record where there was some kind of. There's a lot of fossils that are suddenly going extinct. And these can take place over millions of years. Extinctions can actually take a long, long time. It's just that the rate of extinction massively increases. It's a spike in a graph over a long period of time. That's why they say things like we're actually in a mass extinction right now, because even though you don't see birds dropping out the sky, if you take a longer time span, you think about all the animals that are going extinct during the sort of last few 100,000 years. There's a lot, but it's just spread over time, so you don't necessarily notice it as much, but it's still a mass extinction.
Yeah.
And so one of the first...
shit like hedgehogs and Tasmanian wolf. Tasmanian wolf's gone.
Yeah. Oh no, I've got a whole. I've actually just go into human. I have a table I just pulled off Wikipedia, which is just literally the last 5,000 years. And we've got the last members of a dwarf race of woolly mammoths went around 4,000 years ago. Around 600 years ago, we got the moa and its predator, which is an eagle, died out in New Zealand. Then we've got a few hundred years ago, we got the last wild, whatever the hell that is. I don't even know how to pronounce that. Went extinct, and then along with the dodo, that was another thing. A few hundred years ago, we all know about Steller sea cow, which is just some accurate animal.
Well, there are tons of subspecies going extinct all the time, aren't there? Like butterflies and things we don't notice. And
I mean, apparently, there's obviously projections for extinction rates for things we don't even notice. Insects, particularly, and smaller creatures, which is hard to quantify. I mean, in terms of megafauna, we've got stuff like the passenger pigeon. 100 years ago, died out. Bali tiger.
The white rhino is probably one of the.
The most recent one I've got on this list is the western black rhinoceros. 10 years ago was declared extinct. I think the particular type of white rhino was extinct, but I think there might have been one in captivity, or they might have recovered something there. I can't remember the exact story, but just to give you an idea,
species do go extinct all the time. It's that's not just a human thing. 99% of all species are gone now. I guess the relevance of this is, well, that could have very easily happened to humans. Humans could have just been one of these.
Right. We could have. Are we just in a lucky time period where none of these events that have triggered a particular either massive natural catastrophe, a change in the environment? Again, this is a whole topic that I would actually love to do as a whole podcast, is mass extinctions, because it is a great rabbit hole to go down. And there's a lot of speculation around how they happened and all that sort of thing, which is great fun. But essentially, there are major mass extinctions. I'll mention one of them, the big boy, the Great Dying, which was 251 million years ago, which was sort of in the border between what was called the Permian and the Jurassic, sort of going between the Phanerozoic and the Mesozoic, which is Mesozoic dinosaurs, Phanerozoic stuff before dinosaurs, Cambrian explosion up to dinosaurs, and this during this time, 96% of all species died off just during this one extinction. It's just absolutely bonkers. And it ended up setting the scene for the Mesozoic, where the dinosaurs sort of came up. And one that we probably are quite familiar with is the one 66 million years ago, which was the end of the Cretaceous period, that particular mass extinction in which 76%.
Which one was the meteorite?
Well, that was that one. Yeah, the end of the Cretaceous period. So we that was a meteorite that we found evidence for in the Gulf of Mexico. So we actually have pretty good evidence that it was a meteor that slammed into Earth. And basically, that's what wiped out the dinosaurs and set the stage for mammals, which set the stage eventually for us. And, and then these crazy, weird, big brain creatures that can do mathematics suddenly come out of nowhere. And in the grand scheme of things, that is a tiny fraction of history, like the last couple 100,000 years compared to 4 billion, which is like, since, and think about what percentage I talk about billions of years of bacteria and then like 200,000 years of humans.
I guess there's ice ages and things as well are a part of the extinction.
Right, yeah, massive, environmental changes, supervolcanoes.
You think how fucking hostile the actual nature is. We don't really notice it because we're always fucking sat inside doing podcasts and bollocks. But nature is incredibly hostile, and it's amazing that we're still
right. Well, that's why we have houses and all this sort of thing. Because Christ, we don't want to be, in nature really. But yeah, so to go back to your point, like mass extinctions, like the nature of these mass extinctions could be so many ones that we don't. And again, we're sort of talking about that we have known unknowns. We have there could be an asteroid, there could be a supervolcano. There's also possibly unknown unknowns. There aren't necessarily things that we know about, which we can't really quantify because that's the whole nature of an unknown unknown. There are things we can't quantify that we may have just lucked out on, but we'll never know what those things necessarily were. We just know that there's all these sorts of events that can trigger out massive extinctions and huge changes in the environment that could give, completely almost wipe out. These things can like really rattle life or just send us straight back to, prokaryotes again. Maybe even like a large proportion of multicellular life can get wiped out. And so, these extinction events are a good example of like filters that we've passed, but we don't necessarily have a good idea of how much we lucked out on that. Like, are there things that we should have, we've lucked out since the last couple, as in human evolution timescales? Are we lucky right now?
There's this whole question as to whether consciousness is a evolutionary dead end for various reasons. So we move on from that to filters of the future, I guess. Barriers we're yet to overcome. A large majority of them, I guess, have to do with our own development and our own activity. Does intelligent life lead to self-destruction, I guess?
Right. Well, what's a good example of one of these, like, us destroying ourselves?
Climate change, nuclear war, AI, I think are the big three.
Yeah. No, that's a good little selection of things. Like, there's broadly speaking, there's like technology, which is one category where it's like whether that's like an AI singularity that happens to be something that ends up perverse instantiation, all that sort of thing, and
we talked about
bad things happen, which we've talked about, or even more generally, just like we literally just switch on a machine that's just like a great machine, and we just don't know enough physics, or there's something missing, I think, and we just end up just blowing ourselves up somehow. It's like we just break something without any knowledge of it doing. One example,
that fucking collider thing. The Hadron Collider,
right. Because I remember that circulating in the newspapers. I mean, that was like, again, it was talking about like, there's a 1 in a ridiculous number of numbers chance that it could create a black hole or something. But that was like going off of a theoretical framework that could potentially do it if that theoretical framework.
Well, I don't think CERN would have turned it on. It was like, there's a 1 in 4 chance it could kill us. Oh, go on, do it. Go on, press it. Maybe a laugh.
Go on then.
Banter. No.
That was that's media hype there. I mean, there's obviously cases in history. I mean, before the Trinity test, they had to quite seriously consider, would a nuclear bomb actually just light the atmosphere up and cause an unstoppable chain reaction and just burn the atmosphere off? Like, there was genuine things like that where they're like, do we know physics good enough that this definitely won't happen? They were like, yeah, we're pretty damn sure it won't happen. But it's still something in the back of your head. You're like, gotta just run that through. Just do a few more sums on that one. just to be completely sure that won't happen. And things like this, there are always, again, talking about unknown unknowns. There are things that we could end up developing as a technology that cause a catastrophe and we don't know it. And the second criteria you said was environmental change, like self-induced environmental change, which is another very good one. Obviously, you've got climate change and the certain effects we may be having on our own environment, or even more broadly, we could end up just consuming resources even just outside of the Earth, overly consuming, and then just not being able to just overconsume. I mean, it's fairly simple. That can happen. And the other one you mentioned, nuclear war. So like self-destruction, self-annihilation. It doesn't necessarily have to be nuclear war. It could be like chemical war. It could be anything. But yeah, nuclear war is probably the main one that is most prevalent in our culture. And since the Cold War has been a major theme in sort of existential threats and things like this, and the clock ticking closer to midnight sort of thing. But
I mean, imagine giving that kind of firepower to civilizations of the past, hugely perversely religious societies, like, I don't know, bloody Mayans, or just even just like Christian society in like the 11th century. I was talking about this the other day. There's always some people that frameworks can't really accommodate for. There's always a village idiot, so to speak. And as technology becomes more impressive, it really does only take one idiot. And as population expands, there are many more village idiots and many more villages.
And each individual becomes more empowered with technology as well.
Yeah, we
see like individuals can commit even like far greater catastrophes than they could in the past, simply because of our access to technology now. Scale that up to the extreme, and then yes, you get like one chink in the armor can cause extreme problems. And so these are the idea of like great filters in the future. Filters, obviously, because they're a thing that may be coming up that we need to pass. And the reason why this is like an answer to the Fermi Paradox is simply that the where these aliens went is at some point they encountered one of these great filters that we don't know about yet, and upon encountering it, it wiped them out.
Yeah, Mars used to be the green planet. until fuck knows what.
I mean, that's
somebody pressed a button.
Yeah, and that's one of the most interesting ones, because it's also one of the things like, imagine if we do go out to explore the cosmos and then we find all the evidence of civilizations that have disappeared or killed themselves or died. Would that, that would be like, oh shit, is something going to happen to us?
Yeah, but it would be sobering, I think, and hopefully we'd learn from it. But
I think the problem is we wouldn't know what it would be. Again, it's like an unknown unknown. It's like, okay, they probably did exactly what we did, and we don't know. And if maybe there is no way we could know what happened to them.
I mean, assuming that self-destructive nature on other alien life is, I guess we can talk about that as well. Like that's a problem. Like, you're projecting an idea of cognition and group behavior and all kinds of assumptions about, like, that they're going to have like factions, that they're going to even want to develop weapons, that they're going to want to use them against themselves, that they even have internal conflict. They might not even have a sense of conflict.
In terms of the self-annihilation one, yes. But in terms of like the other great filters we mentioned,
resources,
like technology, technology, resources, we may find that they got to a point where there was a certain technology that is coming up on our horizon, which will kill us, but we will have absolutely no indication that it's coming along, whatever that may be. And so, that would be very sobering, but it would also be very frightening if that was the case. We're talking millions of years in the future anyway. So hopefully, we'll get through that. But yeah, so great filters, the spookiest. That's for sure. So I'm going to break down a little bit of the rare Earth hypothesis. So just as a general idea, and essentially, it's in a way, it's kind of like a new formulation of the Drake equation. In a way, it's sort of like, so if I give you the terms that's in the sort of rare Earth thing, it's like number of stars in the Milky Way, average number of planets in the star's habitable zone, fraction of stars in the galactic habitable zone, and then fraction of stars in the Milky Way with planets. Then we also have, on top of that, we have planets that are rocky or metallic, so to speak, habitable planets where microbial life arises, the fraction of that planet where complex life evolves, and the fraction of the total lifespan of the planet during which complex life is present. So there has to be a certain amount of time that is able to stay there to evolve enough to get to intelligence. And then also this one, which I really don't like, and I think has attracted a lot of controversy, understandable, is the fraction of habitable planets with a large moon. that one being criteria is very much up for debate. That's why I'm prefacing it right now, because I don't really like that one. Is very like out there in terms of like, do we is like there are factors for example like lunar tides, things like this, which are obviously, and also the way in which our moon affect the axial tilt of the Earth, because there was essentially an event during the early Hadean where proposed the idea of how the moon formed was that this another planetary body called Theia slammed into the Earth at the time and ejected a lot of the mass, and then that's what formed the moon. That's also what put us on this axial tilt, which is why we have things like seasons that are not too there's not too much variation in our seasons, but it's also there's enough variation that things like photosynthesis it can be nice, and we can get a little bit of temperature variation. Yeah, so this idea of the moon's formation and the effects that it had on the Earth and the tides and things like this were some very important. I'm sure it was a very important part of how life or complex life evolved on this planet. And sure, it definitely had an effect. As terms of a requirement, that one's really getting out there in terms of like, okay, a large moon being a necessity. I can see why that one gets a lot of controversy. And then there's also the fraction of planetary systems with large jovial planets. And essentially, this is one of those interesting ones where we can start to talk about a little bit like how our solar system is arranged, which is an interesting one because the way our solar system is arranged is relatively unusual in the sense that we have these massive gas giants that haven't gravitated closer to our star and are fairly stable and haven't basically completely ruined the Earth yet, or flung a load of rocks at us. In fact, the way the arrangement happens, and luckily that it is stable as it is, means that potentially that a lot of these jovial bodies like Saturn and particularly Jupiter, important in actually protecting the Earth from a large amount of potential collision events and capturing asteroids in things like that.
Well, you know why that is, don't you? Why the universe is arranged that way.
Why is it, Connor?
It's because it's a gift from God. It's God's grace so that we can survive because we're the center of the universe.
Yes.
This has been a vehicle for Christianity the whole time. Convert to evangelical Christianity. Yeah.
There's the advertisement. Yeah, so that there's all those sorts of factors that sort of factor into this idea of the rare earth hypothesis. Of course, the criticism this particular answer to the paradox sort of attracts in rare earth being so rare that you don't get this intelligent life. It's a bit anthropocentric. It's just kind of describing how life evolves on Earth and then going, well, that's how all life has to evolve, which is understandable. That's fairly.
Well, it is like as much as I'm ribbing a bit, it is like fucking mental. The conditions are absolutely just right. And we aren't seeing that anywhere
to the
else.
extent, although to the extent at which we adapted into particular conditions and the extent to which all possible forms of life could have a slightly different idea of what their ideal conditions are. Of course, that's, again, another key part of the debate is how much are our conditions something that we've heavily adapted to, and how much are these conditions the necessary ones to what are the parameters how far can you go before you can't get complex life anymore, and how far have we gone in terms of like this is just exactly we had to have these exact conditions in order for intelligent life to evolve. And so rare earth kind of goes for the route of like, look at all these things. These are all factors that basically make our situation very unique. If this is the way that life has to evolve, then these very unique set of things that have to happen, and because all these things have to happen, it's very rare, and thus that's why you don't see loads of alien life. Another one that's kind of a bit ropey is things like magnetic field and plate tectonics.
Surely consciousness comes into this as well. We're the only animal that's conscious.
That depends on how you define consciousness. I don't think we're the only animal that's conscious, and I think it depends on how you define consciousness. But that's a whole consciousness podcast.
Yeah, I don't definitely do not want to get into that one. But which animal is it? Is it squirrel?
I think most animals are conscious, and I think that's to do with confusion between the definition of self-awareness and consciousness. But that's the whole other podcast.
So we're the only animal that's self-aware. You would say
there's a limited number of animals that are self-aware, but if consciousness for you is self-awareness. Sure. If consciousness is slightly more nuanced than that, which I'm in that and the sort of Thomas Nagel camp, then it's more. There's a little bit more going on to the idea of what consciousness actually is. So yeah, I don't particularly think consciousness necessarily factors into these things.
But self-awareness is surely an ingredient to, when we're talking about spacefaring and communicative species. So the question is that's another whole hurdle in itself. You've got life, and then you've got intelligent life.
Right. I mean, so I guess it depends on what camp you're in. I mean,
yes,
I would say most people who are, like realists, naturalists, whatever, myself included, are sort of more in the consciousness is emergent camp, which can entail that more likely than not, it's just a sufficient barrier of complexity and intelligence that through which consciousness arises, depending on exactly how you're defining consciousness. So it's like, sure, yes, but I think kind of innately built into it, at least for most people, depending on how you define consciousness, is that a sufficient level of complexity, in essence, alien advanced life and advanced civilization, if they're intelligent and sophisticated enough, thus it follows that consciousness would have emerged. Given that assumption that consciousness is emergent, given a set amount of complexity required.
Yeah.
So. Yeah, I mean that's all sort of. So for me, it's kind of like it's a redundant. I mean, it's a redundant question asking if a totally different form of life. For me, if you're in the emergence camp, you're sort of like, okay, well, it's sufficiently intelligent and complex enough. Thus, there is no reason to assume that it isn't conscious. In some sense, it is the same because there's a complexity requirement from which it emerges. So. Yeah. So there's that's rare earth, whatever. So we talked about great fields. We talked about rare earth. There's another one which is a little one that we'll just, I think we basically covered. It's just that we're too primitive to actually send out messages that are detectable, and essentially that's just to do with the fact that radio waves, which have been blasting into space again for like 200 odd years, maybe they don't even bother like looking for them, or don't have any interest in it because it's such a primitive technology that it's just like it doesn't even like register for whatever reason.
Yeah. It's just like they're not even capable of listening to it. It's not even something they would register as anything. It's just something to them, totally alien as their forms of communication would be to us.
Right.
There's actually one I've got to do with the limits of technology. I mean, you'll know the exact years. How long were we just hunter-gatherers for?
Oh, hundreds of thousands of years.
Yeah, literally, the vast majority of our existence was so stagnant. We literally just sat in caves, chatted bollocks, and ate mammoth. That's literally all we did for so long. And it took us so long just to get wheels and to get just like basic things working. And then I think we assumed that because the curve after that was so exponential. Well, even then there was dips and things.
Yeah.
But that was the last 100 years have certainly been.
Post-Enlightenment has been pretty exponential.
Yeah. We just kind of assume, okay, well, it's going to keep going up. Flying cars. It's that whole 80s thing.
Positivistic sort of progression.
Yeah. And it's like, well, it might not be linear. We might literally just be at the peak now. We might see through toasters and like weird bloody orb Alexa things that talk to you, and that's it. And that's basically as far as we can get. We don't really know how far we can push technology. We don't know if like you were saying, FTL is possible, faster than light travel, or anything. We don't know if our spacefaring attempts seem to have gone relatively okay, but we've only really done a few. We don't really know. I'd like to think we can get to Mars very easily and do that, but see when it comes.
Right. I mean, I'm very positive about things like the current situation with space flight, particularly with stuff like what SpaceX is doing now, and things like Starship are just bonkers. Like they're just incredible machines. And so yes, I guess solar system. The notion of interstellar travel, though, as one of the things that was on this list is like, do we really know the extent to which the technology is possible? And I think there's definitely, we know enough about the laws of physics, and yes, there are gaps in our knowledge, and we don't have a complete picture for how reality works, but certainly we have enough to know that there are hypothetical things that are certainly within the realms of possibility. And I think you can project that quite far with technology from where we currently are. There are obviously things like indicators like Moore's law, but a lot of people would argue, I've seen people argue fairly convincingly that Moore's law, not only is it more of a heuristic, but in many ways it hasn't been slowing down as a lot of people sort of think, because it depends on how you define the sort of ongoing process of computation. And things like GPUs have kind of...
Yeah, I think a lot of people just, they base that on aesthetic. It's like, oh, it's aesthetics. It's like, okay, well, it doesn't look like it's advancing.
Well, there's certainly an argument to be made that computing hasn't really hit a paradigm shift. I mean, the last 10, 15 years it's been more about data and furthering our sort of understanding of how networks and things like this work, and also making technology smaller and faster and more compact. Whereas the fundamental architecture, to a certain extent, and we'll get into sort of exceptions to this, has not really changed. There's been many aspects to it which have simply been more optimized rather than necessarily gone through a paradigm shift. Well, I will say things like quantum computing that are already very much in development, and already things on the horizon that can be a whole sort of new system that unlocks different ways of computational possibilities. Those sorts of technologies are certainly, like, we've got a future projecting these sorts of things in the future. We've got hypothetical things like thorium reactors, and we've got even potentially fusion reactors, things like this. Maybe we'll get to this stage in the future and we'll be like, okay, we know that many of these things are impossible, but there's so many things that we have left to explore in terms of practical technologies that could have a massive impact on humanity, that I think certainly for now we're far from limited in our directions in which we can go, and how that will impact our ability to do interstellar travel, essentially. So yeah, I mean, the technology sort of being stymied at some point, or sort of running out of thing as another possibility. Yeah, I mean, of course, we don't. Of course, it would be arrogant to assume that there is going to be an entirely linear, exponential increase in our sort of rate of technological development. But even if the rate, the rate is not necessarily exponential, perhaps if it is this a more linear graph, then even then there is going to be, over enough time, still enough technological development to unlock certain capacity for interstellar travel and things like this. Even though, like you said, I think given the best understanding we have of physics, it's looking pretty convincing that FTL is just not a thing and it's not going to happen. And talking about answers to the Fermi paradox, I mean, yeah, we'll get more into this in a minute, but one of my actually, let's just blend them together. But one of my major opinions is what the Fermi paradox tells us, at least about aliens in terms of the observable universe, is certainly that FTL isn't possible. Because sure, if we're expanding the search to our local group, or places which are reasonable to be able to communicate with or visit within the permit of the speed of light, okay, maybe life is rare enough or special enough that we can bring the equation down to separate events of intelligent life are not actually as likely as we think to become contacted with. But there's certainly one thing that does seem to be pretty interesting, which is that if it was possible to develop FTL, that technology was possible for intelligent life to develop, given the scale of the observable universe, at very least, surely somewhere in there, because we're talking such a scale that's so much more vast, that surely, I do firmly believe there's intelligent life outside of our past light cone. But if FTL was possible, then it would be difficult to justify the Fermi paradox, because then if they could travel faster than light, why have they not in the whole observable universe? Why is there no evidence for them?
So as I was saying, with the example of us being hunter-gatherers for 90% of our existence, is it not possible that they're just content to stay in caves, and that they haven't bothered building spaceships because our kind of desire to and curiosity is unique to us? Other races aren't curious in that sense. They literally have no fucking interest in doing that. They just stay on their planet dies, and they might build kind of tribal stuff. They just don't bother getting into spaceships because it's, I don't know. So what you're sort of blending here is one, a sort of evolutionary thing, and there's also this idea of that goes into the sort of loss of motivation category. And so one I guess you're unpacking there is this idea that evolutionarily you may bottleneck into a place where
I mean, that's a difficult one for me because
Is that
imagine
is that evolution, or is that is it cultural evolution?
Yeah, there's one point to this where we can start to talk about more like maybe we can imagine beings that evolve in such a way that have more of a technological equilibrium. Perhaps that's a difficult one to figure out, where there would be no evolutionary pressure to develop more intelligence or become sufficiently intelligent that there would be like an arms race of intelligence, which would eventually end up with them inevitably developing high technology.
Yeah.
That's one thing. But I think the main thing you're talking about here is the loss of motivation domain, which is just the idea that simply, are they, as biotic organisms, simply, no matter how intelligent they are, simply not interested in that kind of? I mean, and one is a psychological argument, which is
one I think has to do with it was collective desire as well. Obviously, to actually, it's a great feat. Like, I mean, why did we go to the moon? Why did we bother? I think it was political, and to transpose that onto another species suggests that possibly they have the same political analogs, the same sort of, because it was Cold War, wasn't it? Right? It's like the space race, because I think the main reason,
it was the main reason when it happened then.
Yes,
I would struggle to justify it not happening ever. And I think one of the main things to tease apart here is the idea of whether a lot of these aspects that we talk about, like curiosity, determination, this idea of ceaseless sort of progression or need to discover new things or figure out things, is that an actual inbuilt Darwinian property of humans? Is that like something where if you have evolutionary pressure for advanced life to come out of the ether, surely one of the things that would be a sort of prerequisite of that is there would be evolutionary pressure there would be a selection process by which individuals who are more motivated or curious, or more like those populations with people who were in it, who were more curious, who like decided to explore more, would have an evolutionary advantage and thus be selected for more. So is there it built into there? We'd have to justify an argument in which there would be no selective pressure for certain qualities, such as like curiosity or even competitiveness, or this need to go sort of further or develop more. And if we can figure out a way in which we could get rid of any selective pressure for those types of individuals, sure, maybe we can make that argument. For me, it's like, it seems far more likely that as a prerequisite of human evolution, it makes sense that there is just automatically selective pressure for individuals who, even if it's not necessarily every individual, it's like you just, as a population, human beings want to have this spread of personalities in which the types of people who want to innovate are part of that population in order for that particular population to gain a genetic foothold or advantage. So yeah, I don't necessarily think that these traits are necessarily like anthropocentric, in the sense that I think given a Darwinian mechanism, you can think of a way in which this transcends just being human and actually sort of is more of a deep like evolutionary thing, where it's like it makes sense for that to be a selected property regardless of how intelligence evolves, right? So that's how I'd roughly sort of tackle that. I mean, continuing in that loss of motivation category that you brought up, I think certainly with like later stage civilizations, the three different ones I've sort of gotten written here is, one is hedonism, actually, which hasn't really come up as far as solutions to the Fermi paradox, and hasn't really registered. But one of the sort of crossed my mind as an idea to put out there is the idea that a civilization can get to a stage where the only ultimate goals are sort of satisfied through total hedonism, and thus things like exploration, contact, desire to get more resources is not necessarily, there's no motivation, there's no reason to keep expanding, keep doing that sort of thing, if a civilization gets to a stage where hedonism sort of takes over, and all the individuals simply are motivated by pursuing pleasure in some sense. One idea of this could be that things called like matryoshka brains and things like this, which are basically where a civilization maybe gets to a stage where they upload their consciousnesses and simply just like, chill around a scar. Technology takes care of them.
So kind of like, transhumanist ideas.
Right.
Yeah.
And it's a civilization that just ends up, okay, we've hit the limit now. All we want to do is live eternal lives in these simulations.
Plug in
with pleasure.
Virtual interface.
Great.
Yeah.
What, in that scenario, if they can essentially live virtually eternal lives, then as far as they're concerned, exploration is pointless and contacting other life, and all those sort of factors, those corporeal factors of the world become irrelevant. Another one could just simply be that once maybe a civilization can get to a stage where survival just isn't a problem, like survival isn't a concern for the particular civilization anymore. They can get to such a secure state that it's just, why would we expand anymore? Why would we go explore more? Why would we go when we've got to a stage where we're totally secure, we've got everything we need, we've got the resources we need, we've got the stuff we need. It's very, very related to the hedonism argument, I guess, in a way, but perhaps you don't even need the hedonism element. You just need is there a rational reason for this particular civilization to expand beyond a point if they get to a certain stage where they don't need to? That's another very simple sort of loss of motivation answer to the Fermi paradox. Excellent. So we've gone through almost all the ones I've sort of got on the list. We'll see if you've got any ones I've missed. But I suppose the next one, just to briefly mention again, was just simply the simulation hypothesis, or what's called like a planetarium hypothesis, which is essentially, well, the reason why there's no aliens is because this is a simulation, and the simulation is built in such a way that there's no other aliens. It's just we're an experiment. Like the Earth is just this great big simulated experiment to run through human beings.
See, that doesn't even make sense to me, because it's like, well, there's so much fine tuning and sort of attention to detail for a simulation.
I mean, the fine tuning would be an argument for the simulation, if anything. Whereas, I mean, the attention to detail, I guess, you could argue, but I mean, sufficiently complex simulations, the whole point would be that it would be complicated, or more complicated than our own minds, to a certain extent. So it's one again, it's simulation hypothesis. You can't,
Surely, if you're making a simulation, you would want it to obey the laws of physics and to make sense. Maybe the point in the simulation we're in is that they've done things that aren't actually on the level above. There's some parameters, constants in the universe they've tweaked and to see what would happen, or they've set certain things up in a certain way. The speculation as to is infinite as far as simulation. That's a whole different sort of epistemic category almost as far as the Fermi paradox is concerned. It's just sort of answering it with going, well, reality is not real, so all bets are off. But it's obviously it's saying that. I'm not saying that the people who believe simulation hypothesis are completely stupid. I'm just saying, like, obviously it's one of the real variations of this kind of brain in the there
matter.
There are sort of epistemic qualifications that need to be addressed before you go down that route. Yeah, it kind of invites other questions.
Right, and we'll do a brain of that sort of episode and simulation episode.
Yeah. And possibly political questions with that as well. Like, there's a lot going on there.
Yeah, I mean, we've already got like 3 different podcasts we need to do now. But so let's dig into this probably second funnest one, which is the sneaky aliens one, which has got loads of different ones in it. So sneaky aliens, we simply haven't been looking long enough to detect signs of intelligent alien life. That's a boring one out of the first one. Let's just get the boring one out of the way. It's just simply that we need a few more 100 years. Maybe we're on the cusp of discovering a signal from alien life, but we just haven't quite got there yet.
Like I said, it's been like 50 years of like actual looking, and and our instruments are getting more and more refined. We keep thinking it's that whole that limits technology thing. I think I brought up. It's like that can go either way. We could be on the limit now. We could be. In the far future, we could have like such things we can't even imagine, ways of studying the solar system.
Yeah, exactly. I mean, that's one where it's like maybe you could field that argument in ad infinitum. So it's a difficult one to sort of. It's like the easy counter to that is okay, but when is we haven't been looking long enough? At what point have we been looking long enough and we can make a conclusion, And obviously, we have a certain degree of a pretty amazing amount of technology at the moment, considering we're just like apes. But, of course, in the grand scheme of things, like you said, we don't know how bounded that is. So maybe it is, we are literally just on not quite on the threshold where we are capable of detecting alien life. The next one, which is a spooky one. This is a spooky one. Is so a highly advanced civilization would perhaps eliminates life once it gets to a sufficient amount of complexity. Before that, it doesn't really care, but maybe it's out there, but it's just, as soon as you get to a certain amount of complexity, they're like, nope, you're a competitor now, or you're a threat, or whatever else, and just goes boop, boop, blows up the Earth to make a giant galactic bypass road, like in Douglas Adams, or something like that. They just like turn up, and they're like, nope, you gotta move,
Well, yeah,
it's
this whole if they're godlike, if their levels of technology are so beyond their own, if they don't want to be noticed, they won't be, and also they might just comprehend us as in the same way. You want to build a road through a forest, and you see a nice hedgehog or bird or whatever, and you're like, that's kind of nice, but I've got, at the end of the day, I've got to do this. So it's not necessarily malevolence. They could just destroy us or ignore us from point of view of, well, there's no point.
Yeah, I mean, that's a perfect encapsulation of the next one, which is the zoo hypothesis, essentially, which is part of the zoo hypothesis, which is just like, we're being left alone because we're basically like zoo animals. We're so unsophisticated. We could either be, there's variations of it where we're an ongoing experiment where we're just like a zoo thing that they're just watching, going, oh, cool, look at that happening. Or like you said, they're just on such a different plane that why would they even bother interacting with us? It would be like us, like I said, talking to a squirrel. Like, what's the point? I've got sort of on there like a sort of, if anyone's watched Star Trek, a sort of prime directive thing in a way. Maybe there's like they're so advanced, but for some reason there's maybe some ethical justification for why they don't interact with life. Or deliberately hide from. Maybe there's some ethical reason that they're for our sakes that they're deliberately not.
That would be nice.
Avoiding. Yeah, that would be a nice one. Just like a prime directive-y sort of thing. But obviously, it's difficult to necessarily come up with a rational reason why that would be the case. Although I'm sure people have and probably will. Next one is another spooky one, which is simply that alien life, or for aliens, for an advanced civilization, it's not advisable to communicate with anyone. And in fact, everyone listens, but nobody's broadcasting. And perhaps there is something kind of, slightly ominous in there, in the sense that maybe we're just one of the naive aliens that's like it was a bit sort of laissez-faire with our broadcasting. And in reality, there's very rational reasons why you should be letting yourself known.
In the Warhammer universe, we're the Tau. We're the fucking idiots.
Yeah, maybe. So yeah, that's another sort of spooky one. Is there a reason why perhaps they are out there, but they're just for a good reason they're not communicating because of the dangers of doing so. Pretty much, I mean, sort of similar to what you sort of mentioned in two different points. The fact that we may just have no reference for them at all because it may be so different physiologically. That their whole perception that like they don't perceive, they don't measure or perceive certain things.
Don't we share like a lot of our DNA with bananas?
Yeah, like 80%. Yeah, sort of. Yeah,
and mice and things. So it's like, imagine something that doesn't share our DNA at all, and
a totally different evolutionary path.
They communicate by. I mean, I really like Arrival. I think Arrival is fucking amazing.
I really like that film. Yeah,
just they don't even think linearly. They don't even think like chronologically X to Y. They think like atemporally. That's perfect. And they don't even use that. They use symbols to communicate. And even then, that's like for our benefit as well. And they don't even have heads. They're just like giant feet.
Yeah, what they called like tetrapods or something pods.
Yeah.
Cephalopods. I can't remember. It's like a certain number of limbs, but yeah, no, those designs are brilliant because, like you said, they're so otherworldly, even down to the fundamental way in which they think and see the universe. Where it's like, on such a fundamental sense, they're like four-dimensional beings. They like time for them is a very different thing to how time is for like something so fundamental to our perception of existing. Is a totally different thing to them. And it's a really cool sci-fi idea to have that level of difference in physiology.
It's kind of like that Wittgensteinian thing of if a lion could talk, we wouldn't even be able to understand it. So even if a lion could, I would probably do this on an actual podcast at some point. But just very briefly here, like if a lion could speak perfect English, we still wouldn't be able to understand anything it says because its reference points would be so far removed. I mean, you think of how a Buddhist monk from the 9th century would have thought. So absolutely completely different to how we would think. You take that like times 20.
Yeah, to a certain extent. I perhaps have a slightly different opinion on that. I think part of that does come to, I mean, similar to the points you were making earlier about like genetic relatedness and things like this. Like there's so much sort of programming in us that seems to be, on this sort of archetypal level of like so fundamentally built into us and so still part of the natural world that sort of like hangovers in the way we behave that are completely irrational in the modern, very human world. But there's so many things that really connect to us on a primal level. Not to mention things as weird as like music being like pleasurable. Like something like that is so like kind of abstract in the way in which we react to it, and yet it feels so important and fundamental to us. I think that relationship with the natural world is not something that would necessarily be because of the shared experience of natural creatures.
Is this in reference to talking to a lion or talking to a Buddhist monk?
Talking to a Buddhist monk or a lion or a grapefruit. I mean, grapefruit, obviously, we're getting into like levels where it's like without even a neurology, it's of course that reference point. You have to start really getting down to the weeds of like what do you even mean when you say communicate, because that's pushing some definitions. But I would say when it comes to like the animal kingdom, there are like to say that there isn't a reference point in any sense would be also in a way to say that be a sort of anti-realist position in the sense that there would be no shared elements to the collective experience of different creatures sharing a natural environment. And of course, humans are on a very different plane. Like, I totally get that. Yes, but to say that there aren't archetypal experiences that are shared by a lion in the sense of, running away from danger or hunting for food or being hungry, all these sorts of things that like run so deep in us, in spite of all our, incredible development in our cortex and things like this, like we're still fundamentally, we have this endocrine system, we have fear, we have irrational behaviors.
I think the context for those things are slightly different.
The context is different, but that's what I'm talking about is on this like deep archetypal level. I think. Sure.
Yeah, I think I agree.
Speaking English, maybe not, but it's like I think communicating. If there is such a thing as being able to communicate the same language as something far less sophisticated, it's just the language would be on a very different level, almost emotional level, or an almost like a primal level. To not start to sound too spiritual or anything, but that's my sort of counter argument to that. It's like this idea that we wouldn't understand anything. It's like, well, it depends on what you mean by speak English. It depends on what you mean by communicate.
Yes, yeah. Mentioning temporality again, I think obviously one of the major differences between our cognition and animal cognition is the absence of temporality. I think a lot of animals just live atemporally. They don't have any concept of time.
There's a very, very limited ability to abstract things into the future is the point there. Like human beings essentially discovered the future through realizing that we could plan for things, realizing that if I plant a seed now, my future, this will have an effect on. Things like that, which obviously to us now are so simple, but yes, like you said.
There's no real concept of like memory. A lot of like what we think is memory with dogs is actually just very Pavlovian, and like it's not just because they're doing it doesn't mean they necessarily understand why. A lot of it is instinct. A lot of it is just completely subconscious. I mean, we don't really know, but from what we can ascertain, there's I think I watched a few lectures when I was at university from some of the leading sort of people doing not just animal psychology but philosophy of mind in general, and sort of transposing that to sort of animal thought. And it's just there's no real sense of I think kind of what we were saying, self-awareness in the animal kingdom. It made me laugh. My mate said deers have democracy. It's like,
well, yeah, that's a bit far.
Yeah, it's like, because and it's this sort of David Attenborough-esque thing where it's just like the deer takes a vote. It's like it's not. Well, it's not really, because I know the sort of the deer looks to all the other deer in the herd, and
there's hierarchical programming.
But that's exactly it. Programming. There's no choice involved. They're not really thinking, okay, so I'm going to do this, and it's not. Yeah, democracy is such a. It's like they don't have an understanding of that concept. And again, it just removing like past and future from that, just I think makes it a completely different thing in essence, and it's totally alien.
Right. The idea of awareness of oneself as an independent entity in the world, and that you are an entity along with other entities in the world is that fundamental idea is something that requires quite a large degree of abstraction in order to actually grapple with, like beyond that, like primal archetypal level. I think for me, like like I said, it's just like the only differences for me is like whether the idea of communicating below that level is possible. And I think still a large proportion of what constitutes a human being is beyond the cerebral cortex. It is lower than that. It's embedded in our in our endocrine system, in the deeper, older parts of the brain. Which still have a large effect on how we're wired, how we behave, how we feel, and I think many of those parts are largely shared with other mammals, and for that reason, it depends on what you mean by communicate. Because I think in terms of shared experiences, there are some on that deep primal level. In terms of complex abstraction, obviously the only example we know of that even remotely close to that level of ability to.
I'm not even sure they could communicate about it, even if that was pragmatically possible, because they just do, but we can still think about
to a certain extent. I do think we communicate with dogs. I do think we communicate with our pets to a certain extent. Like, when your dog is like in pain or whatever, what is it doing? Is it, you can say like, it depends on whether you would argue that I would argue that in many ways, like your pet signaling to you in one way or another is a form of communication. And I mean, that for me would, if nothing else, is like one of the main forms of evidence I would say against the idea that it's impossible to communicate. It's like, well, no, because we can share signals that indicate a state of mind to one another, even despite the massive differences in our neurology. It is possible for us to understand some aspect of the internal world of a dog, like the idea of its pain, whether you believe it's experiencing that or not.
I guess we can understand, but they can't.
Right.
That's the real point when we're talking about communication. We can make a dog do things, but I don't think it. I'm not really sure if that's. It's certain. I don't think it's reciprocal. I think it's just us.
No, I think what is the dog doing when it barks when there's an intruder nearby? What is it doing? I mean, you could say it's just intruder barking, but it's like, in a way, that is a form of communication. I mean, the notion of communication, the notion of being abstractly aware of the fact you're communicating are two different things, as far as I'm concerned. Like the notion of being aware of the abstraction of communication and just communicating, whether by incidents or not, like songbirds, like birds will create alarm calls and things which will signal other birds to fly away if there's danger. That that's communication in a broad sense. The birds in the early morning, they're all telling each other to piss off, this is my territory. That's a form of communication. Of course, it's a different question to ask whether that form of whether that is an abstract awareness of the fact they're communicating with another separate entity. Of course, that's a whole different question. But that's a really cool little tangent. Just like the idea that aliens would just be so far removed, like talking to animals, something that is there still some notion of commonality in there. And I still as I've sort of made a slight case where I slightly lean towards the fact that if we assume that there's like some Darwinistic mechanisms involved with an advanced life, then I think there would be at least some degree of common interface or some similar selective pressures put onto intelligence as it evolves, that there would be some degree of commonality in communication. And failing that, purely abstract aspects of maths and things like this, even if the way in which they do maths and things, the way in which they count or even actually do things, sure, the structure might be different, but fundamentally there has to be some a priori consistency to some systems. And in that sense, that can be a way to utilize, constants in the universe will be the same. The definition of a constant is it is the same wherever you are. So you can communicate through use of things like constants and use of things like fundamental properties and logical relationships between like these abstractions that can be a common place. So for me, it's like I'm more optimistic that there would be some ground, but it's understandable. It's very useful to entertain that idea that maybe there is zero. Is it possible that there is no possible common ground, or it's such a completely non sequitur from our own way of thinking? Yeah, so we more or less covers all. The only last one on the sort of sneaky aliens list that I've got, which is kind of a little cool one, is that aliens are in a state of estivation, which is essentially they're hibernating. And the rationale here, which kind of makes sense as a rationale, is you collect loads and loads of resources, and because you know that there's going to be a heat death of the universe, you save all those resources for when there's going to be no resources. So you hibernate. So you just conserve loads of energy so you can last longer into the heat death of the universe. So the idea simply is that, they're hibernating because they're like, well, okay, let's peace out and then we'll use this energy. We'll use the energy when we actually really need it in trillions of years when we're all, the last things are just black holes. And, well, I think trillions of years there's still going to be stuff around, but universal things be along, but entropy will take its course and there won't be very much useful energy that you can use in the universe anymore. There won't be, and thus there's perhaps you could say that they would rationalize that, okay, well, let's use it later. It was a cool little sneaky alien one, why they're being a bit sneaky. And then the final little answer to the paradox, which is the most fun one, is they're with us already. We already know of them. Well, we don't know of them, but yeah, in this room. So, I mean, we laugh, it's a possibility, but it's not one I necessarily subscribe to, but it's a fun one to entertain. What if, they're already, we just haven't noticed them yet, but they're already sort of, among us.
Yeah. I mean,
yeah.
I don't know. It's one of those things, isn't it? The evidence, you have to, your burden of proof, you have to show evidence first for it. And it's like
things like the wow signal, that was 1977, I think, which was a random little radio frequency burst that's still the most likely candidate for if there was a signal sent out by life. Things like this, and I mean, Carl Sagan going to his grave, I think, was like thinking that certain world events were actually aliens because he was so convinced by this the Fermi Paradox, like the fact that there was so much possibility for life in the universe that some things must, the aliens must be somewhere. So there's plenty of ways in which you can maybe stretch the definition of evidence here, but you can make an argument. Well, we got the Fermi Paradox, so it's a possibility. But so I mean, the main question I'm going to ask you is: out of these ones, what do you think is the most likely answer to the Fermi Paradox?
I think it has to do with technology and the lack of it. I don't see any reason why any other intelligent species should want to leave their planet. I don't know.
So is it a technology or a motivation, like a limit on the upper bound, or is it like they get to a certain stage and for whatever reason, why the hell should
I think they're both interconnected. And I think if you look at, I find it baffling that countries like India have a space program, because it's just like, it is poverty. Sort the poverty out. Don't bloody go to the moon. You won't solve poverty by going to the moon. I do think there's obviously, there's a bit of a rabbit hole, but I think there is like a cultural benefit. It's the same with like, why is so much money pumped into sports while people are starving? Well, because in a lot of cases it can get people out of poverty, and it's like the whole.
There's a financial realism, like the economy isn't just like something where you put money into one place. There's like Pareto distributions involved, and also there's logistics, like to a certain extent. And also money just collects at the top, like again, the Pareto sort of distribution occurs, and the way money moves around, if you set up your system in a certain way, you inevitably get these sorts of phenomena coming out of it. And it's
but I think it can inspire lots of people. So there is that, and it's like, education is a large part of it, but also at the same time, it's like, given that it's so difficult, at least for us. I mean, I'm abstracting a lot here, based on our experiences. But like, given that it is so difficult for us to get to Mars when there are other problems, it strikes me as probably more reasonable, or that another species would be so divided and go, okay, no, fuck starving things, fuck all sorts of internal problems. We want to go to Mars. Why? Because there's these few benefits to do with scientific research. I don't know.
So you're assuming. So I want to make sure this is an assumption here. So your idea is that, like, built into that is the notion that they can't reach a stage where these problems are not solved. So do you think that these problems that we sort of see in our in humanity right now, do you think that those are things that cannot be overcome or will continue to project in some form or another into the future?
I think humanity is too diverse to have that unification, and I think it's always going to have to be grappled with. Like I said, there's always village idiots, but there's also, just take the idiots out of the equation. There's so much diversity. It's hard to like police that plurality, to have like dialogue and there's like, you think of like societal differences between people, and I think that those always require attention and resources that I don't think we'll ever have the surplus resources to then take that and go, okay, well no, we've got to do Mars now. It's like, well, we're always have to direct resources at each other.
But I would say that we organise enough on a national level to talk about Mars. I mean, that's what SpaceX is currently doing as a private company, pretty much on their own at the moment. They're making real progress towards that program. They're not some like an entire planet. They are a sort of collective of individuals within a pluralistic system of that's other companies, that whole country, nations, races, whatever you want to call it.
Yeah, I just don't see why another species would be as divided. I know we are, and that's why we do it, and that's cool. I think SpaceX is really cool, but I don't necessarily see why another species would have why it would fracture so much. I don't think you really see that in other species on Earth.
Well,
really?
It depends on these, like social insects, like things like these are obviously very examples on the very different end of the spectrum, but you do see both, more antisocial behavior. So like cats, large cats are a good example of, they're like the least social animals. They're, as far as mammals are concerned, even within mammals, they're just like, don't like, they just literally meet up like once or twice to make babies. I was
literally thinking of cats as I said that. I'm like,
there's plenty of species who are both way more organized. I think
it's when you add self-awareness into the equation. It just seems, I don't know. Again, we've only got one control group to go from. Us. And
so you think that, right? So you think that they wouldn't have problems, but they wouldn't, like the aliens. The reason why they're not, the reason why they're not expanding or whatever, is for some other reason. Some internal reason, or not because of internal reason?
I don't think they would want to, and I think given that it's so hard, I think they would focus their attentions on other things, because there's plenty of things that life could want, and that's just one of them.
Yeah, sort of going into that, loss of motivation thing.
Yeah.
Do you think that humanity will go extinct before we become a multi-system species, before we actually make other colonies outside of the solar system?
No, I think we'll colonize Mars. Outside of the solar system. No, I think we'll go extinct.
Oof. You're a pessimist in that camp. Yeah. So you reckon? What do you reckon? Will it? Of what nature do you think that we will?
Take your pick. I don't know.
Just any one of the above. Natural.
I think.
Self-inflicted.
Like I said, I think it's just, there'll be so much. I think war.
Right.
I don't think we'll actually necessarily, like you said, extinction is slow. I think we will just have a prolonged war and never bother to go outside. I think as we conflict will take focus, and it will just never get around to it, because it's such
my argument against that is
big unified effort to do.
Yeah, but I mean, do you not think that the sort of, it's not really hegemonic stability, but the sort of game theoretic stalemate you get when you have nation states that have nuclear weapons?
There is obviously evidence that we're becoming more peaceful.
Right. Well, do you think that will not hold into the future, in the sense that this equilibrium that we get that enables this degree of peace, sort of on maybe on a knife's edge, but this because of this game theory, do you think that won't hold into the future, and that an actual proper war, like a self-annihilation, will break out essentially?
I think memories are very short, and I don't think it'll be very long before we forget Nagasaki and Hiroshima. And
I wouldn't say it's those things that are what's holding it back, though. It's self-preservation, in a sense, that is the main fundamental mechanism. I don't think
Yeah,
they
yes,
I don't
yeah,
think they
yeah.
care about other nuclear examples in war. I think
Well, no, that's what I mean.
leaders
They
are
don't
just
they
thinking,
don't
I
want,
don't want to blow myself up. Like that is, you know, that's kind of the fundamental game theory that's going on, right?
What do you think is what's your explanation for the Fermi paradox? Which one do you go with more? What's your favorite?
Right. Well, okay. So we'll break down my opinion. My opinion is mostly that there's a large error bars on the conditions for which intelligent life arises, and I think that we underestimate the probability of life, intelligent life, I should say, arising on Earth-like worlds. One factor is because it's just difficult to say how unlikely abiogenesis is, but in part for me because if you look at how long it took for multicellular life to appear on Earth, I think while life itself did appear fairly early on, it would make sense to me that there may well be many Earth-like worlds that get to a prokaryotic stage or some primitive state of life, but not necessarily go through the randomness or required events that spur another level of evolution that allows it to cause that chain reaction. I mean, prokaryotes are still one of the most successful living things, and so the idea that it's necessarily always going to be the case that every world will, within a reasonable amount of time, hit that a eukaryote or a multicellular life stage is not necessarily assumed. So that's part of why I think the reason is. Another one, there's certain factors, like I've mentioned, the configuration of the solar system. I think certain things like this are maybe more important than we realized. And also that intelligence itself may be more random and maybe more weird, given the lack of convergent evolution examples, anything like a human brain. And yes, there are brains, yes, there is intelligence, but the scale at which humans have undergone adaptations in order to text straight into brains is pretty unprecedented and has only showed up in the last 200,000 years, which is a blip in the memory of life itself over billions of years. And so for me, that certainly strengthens the idea of this equation. And I should also mention, I mentioned the FTL thing. I think that if anything, the Fermi paradox is not a paradox for our galaxy, and for these factors that I think there are many factors that just make it really, really difficult, including travel. Space travel just takes fucking ages. Like, it's ridiculous how difficult it is to get around. Even if you're traveling, at some fraction of the speed of, some reasonable fraction of the speed of light, we're talking just vast hundreds of thousands of light years to get to some other galaxy. So all those factors sort of played in for me, helped answer the question of why life hasn't evolved. I think it's unlikely in our galaxy, which means and if intelligent life, I should say, because perhaps I wouldn't be surprised if single-celled life is discovered if the single-celled life has arose multiple times on different planets, and given mass extinctions as well, that perhaps there has been many examples of simple life that has evolved and just not had the time, has just the planet for whatever reason underwent an irrevocable natural disaster that wiped out that particular life. And so those particular things are sort of like, for me, the most sensible. For me, the least assumption sort of go into those, and judging based on all these different factors. For me, it's kind of those sorts of things. And I think going off to more of the other ones, I think it could potentially be a little bit of great filters. If there was a second one, I would put, maybe it would be in the camp of a very, very small chance that would be the case, that there is something that is on our horizon. There's an unknown as far as technology is concerned. And then maybe at a very, very like really out there that we're too primitive or something like that. But almost definitely, it's to me, it's the probabilities of intelligent life coming about due to the factors of things like multicellular life being, we don't know how random that is. Pressures on evolution to actually cause something like a human being to happen, which, again, we're the only example of that particular extent to which evolution takes into intelligence. And also, I think the third thing that it tells us, like I was about to say, is that I almost certainly think there is intelligent life in the observable universe, because when you get to that scale, it's inconceivable that there isn't, despite however unlikely life is. It just in the scale of that ridiculousness, it'd be crazy to say that, but I think that it does perhaps say something about us understanding that FTL, as far as our laws of physics are concerned, is not possible. And I think, if anything, maybe it is evidence that faster than light travel is even more evidence, actually, to the case that faster than light travel is not possible, for the fact that if it's so likely that somewhere in the observable universe there is alien life, then, and they haven't got to us through some FTL mechanism, or there hasn't been any evidence sent to us through FTL, then maybe that's a case that FTL is impossible. And I think I don't think that's an unreasonable assumption to make, that we are at the limit as far as the speed of the universe, the speed of causality is concerned. Those are essentially kind of my main takes on the Fermi paradox. And I would say there are some weird factors that I sort of think go into it. We may make an entire podcast to name drop a fourth one on the anthropic principle, but there's certainly an element to survivor bias, in the sense that there's to a certain extent, because we're the only example, it is extremely difficult to make really any kind of assumptions about this. And I think, that's one of the major takeaways that most people sort of in these fields perhaps have about the Fermi paradox, is that if you think about it too much, you're doing too much thinking, because you're extrapolating too far into error bars and things that cannot be really quantified probabilistically, which is, sensible to make. Not that discussion to this extent can't be productive or frankly really interesting. So yeah, I those are sort of my main takes, I guess. I mean, also, I sort of briefly mentioned mass extinctions. We'll do a podcast on those, I think, because those are really interesting. And I think the more you look into mass extinctions, I think for me that's another, probably slightly lower on the list than the other ones, but that's a bullet that I think we have dodged to a greater extent than perhaps we realized, in terms of the implications of these natural extinction events that occur relatively periodic, even over huge time spans, but relatively frequently, that you get these massive extinctions. So yeah, that's sort of my take on the Fermi paradox.
Nice.
Yeah. You good?
Yeah, I mean, we can end it there. Just going to say that I think it fascinates me more so that it encapsulates the imagination so much. That people, aside from the details, people are obsessed with this question. I guess one thing we really didn't touch on was the social and cultural implication of it, if this was ever solved, if we ever saw aliens,
or if we get to a stage where we've seen so much of the galaxy and maybe even our local group, and there's nothing, and we're the only ones in it.
Do you think there could be like a paradigm shift coming from that? Do you think it would massively change human?
My hope would be that we would treat our existence and life and we would as a way, at a level of importance that's extremely profound. Because
if we found nothing, yes, because it's like literally with
it's our ethical imperative to preserve what life we do know exists. I mean, for now, that I still think that's our imperative, and I think we need to get off this earth as quickly as we fucking can.
Yeah, and the byproducts of that life as well. Every tradition. I mean, I'm quite a preservationist in a lot of senses. I don't know if I'd say like socially conservative, but I there's a lot of like old things that I just think it's such a shame when they do die out. It's I think I mentioned on the very first podcast, there was a guy who was using like bellows and like an old fire to do like smithing horseshoes and things. He was like an old farrier. And just seeing those kind of old quirky things just die, it's kind of a bit of a tangent. But I think that just literally
extrapolated to an entire civilization.
Every product of life is just like the millionth chance of being. It's just incredible. It's staggering. But I don't think people really want to stop and think about the fortune that is existence.
Right, and the potential, the potential amount to which it is extremely special in the universe. We don't know because we simply don't know how special we are. And yeah, like I said, I think exactly the same. It's like the implications of that should hopefully mean that we are motivated to, survive at very least, and try to create an ethical, preferable situation for ourselves.
On that note, I think we'll end it there. A nice second lockdown, everybody.
Farewell.
Cheers.